In this video, we are going to look into solid phase extraction. And one of the last things we talked about in the last video in the liquid-liquid extraction was that in spite of being a very efficient, liquid-liquid extraction has the drawback that very large solvent quantities are often used, which is not very environmental friendly. Additionally, it's not very well automatable very often. And these are serious drawbacks which have made solid phase extraction at least equally popular, I would say, in the last 2 decades, actually more popular than the liquid-liquid extraction. The balance maybe has shifted a bit after the introduction of Getter's method. So for liquid-liquid extraction in a tube methods introduction, but still solid phase extraction is a very, very powerful method. So what does this solid phase extraction actually mean is that we use a solid to extract the compounds from a liquid sample. So the sample is a liquid, similar to liquid-liquid extraction, but the phase where we want to extract our analytes to is a solid. And with this, we aim to concentrate the samples, concentrate the compounds that we are interested in, so our analytes, and remove the components that we are not interested in, so the interfering matrix components. So sample purification is very, very important step here as well. Solid phase extraction often helps us to concentrate the samples. It can, however, further be coupled with concentrating the samples further, and it can also help us to do solvent exchange in cases where the original sample solution is not suitable for the analysis due to the instrumental limitations. The heart of solid phase extraction is a solid phase tube. Actually, we very often use SPE instead of saying out whole solid phase extraction. So I will be doing that in this video as well. So the first part of this, the heart of this is an SPE tube. And let's maybe look at this schematically. So first we have a sample that is in a tube or a flask or something like that. And this contains analytes if we have any internal standards, but also internal standards, and of course the matrix components. The SPE tubes are phases where we have our solid phase, so the phase that is used to extract the analyte from the sample. And this solid phase here is usually placed in a syringe-like carrier, but the syringe itself is inert, but it's inside the syringe. There are small particles of the solid phase that is then having affinity towards our analytes, and these analytes bound then to the solid phase due to this affinity. And the solid phase is kept in the syringe by having 2 filters, one below and one on top of it, so that the solid phase would not move when the sample is being added to the solid phase tubes. So the first thing actually that happens is conditioning of this solid phase tube. So this usually means washing the tube and conditioning, which means that we prepare the solid phase to extract the compounds of interest. Usually we first wash with some kind of organic solvent to kind of wet the solid phase, and then wash with the same solvent that our sample is in. So if we are extracting, for example, water samples, then the washing solvent is also water. Thereafter, we apply the sample, and the aim here is that the analyte molecules are retained in this SPE tube. So this means that they are interacting with the solid phase particles in this SPE tube, and they are staying on these particles, and they do not flow through the solid phase extraction tube while the sample is being applied. However, matrix components can move through already when we apply the sample, or when we wash the solid phase tube directly after introducing the sample. So we can wash the cartridge with something that is not carrying through the analyte, but washes through the matrix components. This is based on the assumption that the analytes are interacting stronger with the solid phase than do the matrix components. After that, we can apply a solvent that is now strong enough to extract the analytes from the surface of the solid particles, and we can collect the analyte when it elutes from this SPE tube, so when it is extracted from the solid phase particles that are in this SPE tube. And later we can do other modification where we can either dilute or concentrate. We can analyze it with HPLC or GC. But these are the main steps of doing the SPE. So another alternative process is that we could use SPE just to remove the interferences. So this is a lot less used because this does not allow concentrating the sample. In this case, we have a similar SPE cartridge or tube, which is filled with a solvent. But in this case, the interfering molecules have affinity towards the solid phase, and our analyte does not. Similarly to this case, this cartridge, the solid phase is washed to prepare it, to wet it, and then the sample is applied. But now the cartridge, or actually the solid phase in this cartridge, has affinity towards the interfering compounds. This means that when the sample is passing through, the interfering compounds stay in the column, but analyte molecules flow through. And this sample we can then collect and analyze. This is by far less often used possibility, but this can still also be applied. The apparatus for doing solid phase extraction can be different. For one sample, it is possible that we have here this SPE cartridge where this solid phase is that has affinity towards our analyte. And here we press the sample as well as the solvent through this cartridge simply by having a syringe on top of it. So we simply add pressure, and then our liquid sample flows through the SPE cartridge. If we have just one sample or very few samples, then we can also use a single sample manifold when we put the cartridge here on top of a conical flask that is then connected from here with a vacuum or a vacuum source or a water pump, for example. And then we pour our sample just on top of the cartridge, and it flows through due to the reduced pressure here in the flask. However, mostly we have many samples, and the SPE's advantage towards liquid extraction is really large if we have many samples. So in these cases, we use kind of manifolds which can have 10 to 40 different, or not different, but which can enable extraction of 10 to 40 samples at the same time. So how this works is that there are individual carrier spots for different cartridges, and we can introduce to each cartridge a different sample. So this means that we can actually do samples in parallel. And this manifold here has usually of glass made container, and this container is then connected to a vacuum source, like a vacuum pump, for example, which is then used to actually get the sample as well as the solvents through these cartridges. The cartridges are not, they are very similar to liquid chromatography columns, but the particles are much, much larger. So they don't actually require high pressure, but at atmospheric pressure, the flow through is extremely slow. So reduced pressure on the under the solid phase cartridge is needed to actually get reasonable flows of the samples through the cartridge. When we look at, let's take a closer look at the cartridge itself, then it is usually, as told, a syringe-like system. It can also be kind of a syringe filter-like system, but mostly it's a syringe-like system. It has a small reservoir here on top, which can have then the sample or part of the sample, or also the solvent. And there are two frits or filters that hold the sorbent in place in this syringe. So now, how and why are these compounds actually absorbed by the solid phase that is in this cartridge? This process is actually also very similar to liquid chromatography. It can be either based on hydrophilic, hydrophobic, or ionic interactions. And we can think of this also as retention, but here the retention must be much, much more strong compared to HPLC. Because in HPLC, we wanted that our compounds all move, they just move through the column with different speed. But here in SPE, we want the compounds either to stick to the solvent, this is when we introduce the sample, or to completely elute from the sample. This is what we want for our analytes when we are extracting them out again with the solvent. So it's very similar to HPLC, but we want in the introducing the sample stage, we want that the analytes would have a very high retention factor so that the K values would be very, very high. But when we elute it later from the SPE cartridge, then we want that the elution would happen very fast so that we would not need to use very large volumes of the solvent to get all of our analyte molecules out from the SPE cartridge. So therefore, SPE is kind of an on-off HPLC. In the sense that on is when we introduce the sample, all of our analytes need to stick very, very strongly to the solid phase, to the kind of SPE column, while when we elute them out, then we want everything to elute as quickly and as efficiently as possible. We don't want any kind of slow processes here. So this is the difference between the solid phase extraction and the HPLC. So what in the sense of retention factors in SPE, we want that when we introduce the samples, the retention factors would be 1,000 or higher, and when we elute it, we want it to be extremely small. In comparison, in HPLC, we wanted the retention factors to be mostly between 2 and 20, or even better 2 and 10, so that we would really have kind of continuous movement of the analyte through the column. And this is something we don't want in SPE. The question now comes, how to choose the solvent for our solid phase extraction extraction procedure. If we are combining the SPE or during the sample preparation via SPE before the HPLC analysis, then it is good that we use a different mechanism in SPE than we use to actually separate the analyte molecules in the HPLC. If we are doing GC analysis or just mass spec analysis or something like that, then it's not so important. But in case of HPLC, because this is also kind of an SPE, this is also kind of a liquid chromatography in SPE, it has proven more selective when we use a different chemistry to actually extract the compounds. And this is because if we use, for example, reversed phase both in SPE and in HPLC, then the compounds that are retained similarly to analyte in the SPE would also be the same, which would coalute with our analytes in the liquid chromatography and could therefore interfere. So we don't really get much of a separation here. However, even if we are using LC, this is not always possible, and sometimes you do end up using the same kind of separation in the SPE and in the liquid chromatography. And to choose the suitable solvent material for the SPE, we need to consider both that our analyte retention in the SPE cartridges would be strong enough, but we also need to consider what are the matrix components that we need to get rid of, so that these matrix components would not retain that strongly and would elute nicely as much as possible. So the solvents that can be used could be inorganic oxides, for example, for kind of normal phase SPE, and here the terminology is the same as it is for liquid chromatography. Here normal phase, reverse phase mean exactly the same kind of interactions as in case of liquid chromatography. So it can be a kind of normal phase type with inorganic oxides, or it can be a solvent with bonded phase, which is then type of reverse phase chromatography kind of SPE, but it can be also other types of bonded phases here used. It could be an ion exchange, and actually in comparison to ion chromatography, ion exchange SPE is proportionally more popular. That doesn't mean that ion chromatography is not used, it is used, but ion exchange SPE is much more popular than the ion chromatography would be. There are also kind of mixed type solvents, so that means that we could do both helic and reverse phase in combination. And there are also some very specific techniques which involve having internal surfaces inside the particles that would have different chemistry than the outer layer of the particles. So let's dig now into these different mechanisms. So inorganic oxides are mostly silica or aluminum oxide. So they are kind of normal phase chromatography solvents. And in these cases, our sample is inorganic solvents, and we are trying to extract, or we can extract with this normal phase SPE, the compounds which have some polarity. So our solvent should not have any polarity to not compete with our analytes, but the compounds should have some polarity to interact with the solvent material. It can be a problem that some of the compounds adsorb to the solid phase. So this means that the interaction between the analyte and the solvent is so strong that it would be hard to elute them, but this sometimes can be overcome with adding a small amount of water to facilitate the solution. Most simply, this kind of interactions incorporate hydrophilic interactions with the sidanal groups and then the polar part of the molecule. It's important, however, that the compounds that we need to get rid of would not give these hydrophilic interactions. Otherwise, we are actually not really separating between the matrix components and the analyte during our SPE process. A very popular type also is reverse phase SPE. However, this is by far not as popular as is the reverse phase in the HPLC. And this is actually logical because the SPE it would be good if the SPE would be of a different separation mechanism than is actually our HPLC column. So if our HPLC column, so if we are already using a reverse phase HPLC column, then it's logical that we would like to choose a different kind of SPE separation to concentrate our analytes and actually remove them from potentially interfering compounds in the HPLC. However, sometimes still reverse phase chromatography is used. Reverse phase SPE is used in the SPE process. They are very similar to the solvents in the HPLC. C18 is very popular, but also biphenyl, for example, when we deal with aromatic compounds, or for slightly different mechanism, cyano groups can be used as bonding phases. This is when we also want to add some part of the solvent analyte interaction of a pore type to the retention mechanism. And the carrier to which these groups are bonded can be both silica as well as polymers. So in HPLC, we actually almost never have polymers as the carrier because they are usually too soft. But in SPE, where we don't have high pressures, the polymers are actually even more common nowadays than the silica carriers are. C18 and C8 are good to determine organic matter from water or very water-rich samples. So this can be, for example, determination of some pollutants from drinking water, or some drugs from urine, this kind of separations. And sometimes also, if the matrix is an inorganic solvent, then we could also add a bit of this polar interaction with using then cyano or even amine or diol groups as bonded phases in the SPE. It's also possible to use ion exchange, and there are both strong and weak ion exchanges, both anion exchange and cation exchange. Weak anion exchange, for example, is denoted as VAX, while strong is denoted with SAX, and the corresponding cation exchanges are then VCX and SCX. And these are actually very common abbreviations when you look at the SPE materials. The idea is that if our analytes do have some acidic properties, then we can use anion exchange to concentrate our analytes by changing the pH so that our analytes would be in the anionic form. And if our analytes are some bases, for example, very many pharmaceuticals have some basic groups, then we can change the pH so that these bases, usually nitrogen bases, would be protonated, and they could be separated with a cation exchange. So for example, if we have now an analyte that is cationic, then we could have on the particles, on the SPE material particles, some anionic groups, and then these anionic groups would interact strongly with our protonated basic analytes, and therefore would retain them when we introduce the sample to the cartridge. In case of acidic analytes, we would, however, have here a cation on the surface of the solvent material, and our analytes would be anions. But the interaction between the analyte and the solvent material is of an electrostatic nature in case of ion exchange SPE. Nowadays, it's even more popular to have kind of mixed type solvents. This means that we can combine two different retention mechanisms. A very common one is to have some kind of an ion exchange in combination with having a reverse phase bonding. It started actually in determining pharmaceuticals from biological samples, because very many pharmaceuticals are acids or bases, but they also have hydrophobic moieties. So the idea was, why can't we use both interactions together? Especially because we are using here a kind of an on-off mode, so we could actually get rid of both compounds that interfere due to being absorbed with the reverse phase, or due to being also absorbed with the ionic chromatography, ionic SPE that we would use normally. And this turned out to be very, very popular. So for example, this is now also widely used in determining contaminants from water samples. This is kind of a standard preparation also for this kind of samples. And here the bonded phases are of two different retention mechanisms with the analytes. One more interesting as SPE type is an internal surface reverse phase. And this can be